Impressions from the AI summit that I just attended. I attended a 2-day summit about edge computing and hardware for AI. And these are my impressions. I want to try to be concise, but I might have to use 2 episodes. I'm not sure yet. I'll just start going and then see where it goes. I want to talk about 2 big trends that I saw. One is the merge of edge and cloud into one. So the edge, whatever the edge is turning into part of the big compute paradigm, which is that we have compute, which is provided by the cloud. There was a lady from AWS talking about this. I want to talk about that. The other big trend is neuromorphic compute, the attempt to compute with less power, less energy, and still get the job done. And that neuromorphic compute is one of them. There's a couple of trends here that are very interesting. One is on the edge. So at a small scale, we want to have devices that can solve I call it neuromorphic compute just because it mimics the human brain. What the human brain is able to do is do amazing amount of compute with very little power consumption. So how can we achieve that? We can do 4 things. One is on the hardware side. We can work towards sparsity, low precision, and quantization, and then we can build algorithms such as the equilibrium network algorithm or a prediction programming. Those are things or routing, which is what Cerberus is doing, or GraphCore, I forgot, no, excuse me, it's GraphCore. So what they're trying to do is the following. You have these massive, on the big scale now, we have these massive chips, and we're routing the input towards local areas of compute. So this is kind of the idea. What neuromorphic chips are trying to do is find a way to either route the input to the most suitable nodes or to have some sort of implicit function, they call it energy function, which only uses the nodes that are relevant for this particular input. This in itself opens up a whole new conversation about the routing algorithms or about ways to define this input belongs to this node. So those are interesting problems and very beautifully, again, Popperian, of course, in a sense that we are solving the problem of the new workloads of AI and we're creating new problems which are interesting. This is the Not Even Wrong podcast. It's September 14th, 2022. This is Krim Delco for the day. The fund is up 2.8%. The market is up 30 basis points. For the year, we are down 24.7%. The market is down 17.5%. We're underperforming by 7.2%. I am finishing my 2-day stint at the AI Summit here in Santa Clara. A beautiful experience in person with people talking, and I want to share my experiences here. And like I said in the prelude, the 2 things I want to talk about in this episode. One is the merge within the compute world of edge and cloud towards one big system. This was discussed by AWS, and I want to keep talking about this a little bit, and it's related to the second one, which is the idea that we, particularly on the edge, start coming up with ideas where we can do compute and learning, particular learning, and do that with little power and little consumption of resources, because of course in the edge we are constrained. So those are 2 interrelated developments, and what I've noticed is particularly on the edge. On the edge, well, let me start with the second one actually, the edge side of things. So what I've noticed is a big effort to diversify the compute space. So meaning we don't just have the CPU and we don't just have the GPU. We are having all kinds of things here, from the small to the big. Lots of vendors, interesting applications. We have people that are improving the current CPU space with, let's say, software-defined CPUs. We have people that are using RISC-V now actively to make CPU consumption a lot more energy efficient. Then we have whole new hardware endeavors such as Cerberus and GraphCore, the two big ones that were here, but there were other ones, and of course the traditional vendors like AMD with their FPGAs, they were present with FPGA, with their Xilinx offering. So we had a lot of these different types of ideas being presented here. Then the neuromorphic side of things, which I was pretty excited about. What is that? Neuromorphic computing is the idea that you use a lot less power to get the job done. This is the idea. And there are 4 levels of vector, or 4 attack vectors here that you can use to achieve that. You have 3 on the sort of model hardware side, which is you try to work with sparsity, you try to work with low precision, and you try to work with quantization. And then you have the 4th, which is a model thing, which is you come up with new models. And the idea here is that you're thinking, look, how can I channel my input to the right nodes so I only use the nodes that are most efficiently used in this particular instance when an input comes? Because as far as we understand the brain, this is what the brain does. The brain has the ability to localize its work. It's not like when you see a beautiful woman walk across the street, it's not your whole neurons that light up. It's only locally. And that is what goes on across the board all the time. So this is, in a nutshell, the idea. And again, the way it's done is by having either a routing algorithm that takes the input and routes it to the proper node, or we have some energy-based algorithm that is able to basically turn off all the unnecessary nodes and focuses only on the nodes that are relevant for this particular input. So this is what neuromorphic computing in general means, and what is part of this endeavor to get the edge more intelligent, in particular learn. Because what I thought was very interesting by Jordan, the CEO of Ray Neuromorphics, is he said, look, and it's something that I never thought about. We are learning in the cloud, and then the inference is done on the edge. And that's fine, it works, but why not do both on the edge? Why not have a car? Why not have a Tesla learn and infer at the same time? Because that's what we humans do. And if you think about it, isn't that much, much better? So that we have more adaptability, we could have a little bit of the plasticity that Edelman's talking about all the time in a robot. So the idea that we can learn and do inference at the same time, I think, is absolutely key for a more plastic intelligence in robots. So this, to me, this is very exciting. I don't know about this particular company, but the idea that we have more plasticity, I think it's interesting, and it's something I want to bring up to Tesla on the AI Day, hopefully, if I get invited, and if not, I'll try to bring it up in some other way. So having said, now these are these endeavors, this is the endeavor, so neuromorphic compute is on the edge. And then we have the endeavor at the big scale, which is the big guys, if you want, the GraphCores, the Cerberuses, and all the other big guys, NVIDIA, of course, that are working towards solutions that can allow for massive, massive compute. And this is, of course, confined to the data center, massive power consumption. And the presentation by GraphCore was very inspiring, because what GraphCore did is basically show a timeline of how we can go towards 100 trillion parameters in a model. And I thought it was very useful to give a number on, okay, what are we talking about when we talk about large models? And I think we can quantify this, but this is the amount of parameters we want to have to really, really be able to do large-scale compute. This was very helpful. And in order to solve the problem here, we have to have, according to the person, I forgot his name, Phil was his name, I believe. So what he said is very interesting. He said we had these three levels of AI in the history of AI. Started with supervised learning, data was the big cost. Then unsupervised learning, compute is the cost, and the third is the transformer models where we are today, and there we have we need memory is the bandwidth, the memory bandwidth is the problem, and therefore we need to solve the problem by having what he calls a routing network. So we route the input towards the right nodes, so we don't use all the nodes at the same time, because if we had 100 trillion nodes, according to his calculation, maybe we'd use something like 65 gigawatts per year to do a compute, and that's just not feasible right now, at least not with the cost of energy where we are today. So that's on the big scale. And again, what I find interesting here is that we have developments on the big scale and developments on the small scale, and the ecosystem is growing on the small scale, meaning on the and if you want to actually, big and small is the wrong word. I think let's just talk in terms of power consumption, because I think this is what it's all about. So we have endeavors that are trying to reduce the power consumption by either using neuromorphic compute or some sort of more intelligent way to compute on the edge, and particularly do learning on the edge. Then we have software-defined, let's say, CPUs. We have RISC applications such as RISC-V, company Sci-5 and others, where they're offering their instruction set architecture based on RISC-V. So RISC-V is the idea that you can do compute on a CPU using the von Neumann architecture, but with much more efficiency, and therefore use less power. So those are sort of the endeavors. I think, let me now talk about another panel that I attended, which was really interesting, talk about software-defined hardware. It was actually about software-defined hardware and co-design. And there was this person, Charles, from Memworth, a company that does software-defined memory, and he said something very interesting. He said that we have the three big bottlenecks in AI today are, one is compute, and then one is the von Neumann, the second is the von Neumann wall, which is the interconnect between CPU and memory, and the third is the I/O wall, which is the interconnect between CPU, memory, and storage. And he said we can solve for all those three by using better technologies, better interconnects, and all those sort of things. But I think what's really interesting in the software-defined hardware space, and this is, again, this kind of reaches across this conference, that you can come up with new hardware like Cerberus and GraphCore, and that's a good thing. But you can also try to use software to help. And what these people in the panel, there were other people in the panel, they were not very impressive, to be honest, but Charles was very impressed, because he said it the way it is. He said the biggest wall is the von Neumann wall. The von Neumann is CPU to memory. This is exactly what Onur Mutlu is talking about all the time. So this is the biggest wall we have. And the way we can solve it is, right now we have a very practical solution, which is CXL, which is a protocol that is designed for the interconnect between CPU and memory, and I believe also memory and storage. But let's CPU and memory. Let's focus on the von Neumann wall. So the von Neumann wall is the idea that in the von Neumann architecture, you have constant move from memory to CPU, back and forth, and that is very energy intensive, and to some extent also time intensive, performance intensive, and all these kinds of things. So that's what Mutlu is talking about in a lot of his lectures. Try to solve that problem with in-memory computing, meaning having logic in the memory so that you don't have to go to the CPU. Now, I spoke with people on that panel. They were very skeptical about that. They believe that that is not a good solution for now. But this protocol, which is fairly new, is so CXL. I'm going to have I keep an eye on that. That is a very interesting concept. The other concept that they were talking about was the idea of software-defined hardware as composability and disaggregation, and those are two buzzwords which I think are incredibly important. Composability, disaggregation. It kind of solves the Onur Mutlu problem, and Onur Mutlu starts his lecture on computer architecture. He says you should think up and down the stack. And that's obviously logical, but how can you actually execute that? What does that really mean, up and down the stack? That means that you think about the software applications, and then you think about what kind of instruction set architecture you should have, and then you go all the way down to the logic gates almost, and then you adapt to whatever the workload is. Because let's be clear, in the end, the most important thing is the kinds of workloads that we're having need to be executed by the hardware. And the solution, according to Charles and his panel mates, was to have software-defined hardware composability and disaggregation, which I think is fantastic. So that's another thing I want to keep an eye on. So I want to keep an eye on particularly two things. One is CXL and the other is composability and disaggregation. So this is very interesting indeed. So those were I think that those are the big takeaways from this AI and hardware summit. To summarize, we have software-defined solutions for the von Neumann wall and the I/O wall. We have a merge of the cloud. We have a merge of the edge and the cloud towards one big system, which is driven particularly by two innovations. One is edge learning, so we can have learning on the edge, driven by things like neuromorphic computing, but also other endeavors, but neuromorphic computing. And then we have also better interconnects, and again, software-defined networking, of course, which is the idea that you can have. There was a person that was talking about the different layers of connect. So from the edge for embedded computing, and then MEM, which is sort of connects next to the cell towers, and then you go all the way to the cloud. So you have these different levels of connect, and 5G is driving a lot of adoption towards, let's say, having compute happening at the cell tower level, so you don't have to go all the way back to the cloud. So there's a lot of different positions you can put compute and memory and storage, and therefore go towards a kind of integrated cloud from the edge towards the cloud. I spoke with a lady from Amazon Web Services. She absolutely seconded that, and that was a very interesting. I think when I was on that panel about software-defined hardware, I asked myself the following question: what would John Von Neumann say about today's compute environment? I think he would say, why are you guys still using this compute environment? Why don't you use a new paradigm? Because the paradigm that I came up with, where I have this memory, program, CPU, storage, I/O, this was based on the idea that we have programs that execute. And now we have a different programming paradigm, which is we write algorithms that are fed data, and then the data writes the executable through the algorithm. So that's very different. And in my point, it requires a different compute architecture. One solution is this composability and disaggregation, which is software defined and therefore flexible. Another solution would be a new computer architecture. I tried to talk about this. People were a little bit skeptical, didn't really want to engage in that, because that's obviously way too academic right now. And you're at a hardware vendor conference and you're telling them basically the whole compute paradigm that you're building your business on is wrong. Doesn't go well. But I think it's a nice idea. It's a good idea. And I think finally what I want to say is the purpose of this podcast is to give people a sense for what it feels like to run a hedge fund. So it's incredibly important for us at Orange Capital Partners to do these types of conferences, to be present. And particularly, this was a conference which was driven by tech people, engineers. This wasn't a conference about money. There were lots of VCs sniffing around. There probably were hedge fund managers. I wasn't the only one. I know, I'm aware of that. But nevertheless, I just want to convey this again. Hopefully, listeners take my comments here not as investment advice. It shouldn't be taken. This is just simply, I want to give people a sense for what it feels like to run a hedge fund. And I think the reason these types of conferences are so important is because they give us a feel where the rubber meets the road. And this is where wealth creation starts, by understanding where technology and science are meeting towards producing products and services that can be used in businesses. And hopefully sometimes it actually has a very big impact, and that's where the big wealth creation happens. Thank you.